This video, we are going to look at the use of the sum and difference formulas and patterns that we notice when we're multiplying complex numbers that are in the polar form. So let's just say, and then we're going to get into a proof with this. We're going to get into a proof, the fun proofs. So let's say I'm given three values. Z1 in this case is equal to 2 CIS pi over 4. Remember, cis is, in this case, is for cosine, and then the imaginary sine, pi over 4, with 2 being our radius. Our second number, actually, let me do it. I could play with different colors, so let me do a second color. Z2, that's bright, is equal to 2 CIS negative pi over 4. And the third one, I think I'm going to pick a blue for this one. Z3 is equal to 3 CIS pi over 2. All right, so we're going to multiply the first two together, just the first set, just to figure out this pattern. So I'm going to do 2 CIS pi over 4 times 2 CIS negative pi over 4. All right, breaking this up a little bit, we're going to get, I'm going to pick a different color. I'm going to pick green. What this really looks like is 2 cosine pi over 4 plus I sine pi over 4 times 2 cosine negative pi over 4 plus I sine negative pi over 4. There's no reason I put parentheses around this cosine and not the others. I just, in my mind, thought of this parentheses and put it there instead. 2 times 2 we have is going to be 4. Cosine pi over 4 is root 2 over 2. Sine of pi over 4 is root 2 over 2 I. Then here, I already did the 2 times 2. I converted those into coordinates. This one is negative pi, so we're going in the clockwise direction. And so we are in quadrant 4. And in quadrant 4, y is negative, x is positive. So cosine is going to be positive, root 2 over 2. Sine is going to be negative, minus root 2 over 2 I. All right, so then when we multiply this out, we notice that these are conjugates of each other. So we're left with 1/2. So root 2 over 2 squared would be 1/2. We have the I here. Remember that I squared equals -1. So even though this is a positive times a negative, we're also multiplying it to a negative here. So positive 1/2, which this is going to be 4. And if I were to write this in the polar coordinate, this would be 4 CIS of 0. And this comes into play when we look at the second one. And this is basically because 4 is on the real axes. So we're looking at when theta equals 0. Or 4 cis 0. Okay, so I'm going to have to use my eraser here. I did not plan this or coordinate and make this into a different layer. So we're going to grab my eraser. We're going to make it a little bit thicker so that I could get through this a little bit faster. And just erase. My sound effects. That's my erasing sound effect. I don't know why shh is my eraser sound effect. That's a very interesting idea on why. Well, shh. but that's what I do, and that's what we're going to do. So the second one we're going to explore here is we're going to do the 2 let me learn from my last mistake. Let me just add a layer in here. Let me just grab a new layer so that it's not with the original layer. And I'm going to say 2 CIS negative pi over 4. And we're going to multiply that to 3 CIS pi over 2. All right, now what I'm going to do here is right away, I noticed on that last one, when we multiplied the 2, we got, when we multiplied Z1 and Z2, we got 4 because we multiplied the coefficients. I do that right away. So I'm going to have 6. And then I have CIS negative pi 4. And then CIS pi 2. All right. So thinking of cosine negative pi over 4. Cosine negative pi over 4 is going to be root 2 over 2. We already talked about this. Minus root 2 over 2i. Because sine of negative pi over 2 is in the 4th quadrant and sine is negative. This one we're looking at cosine of pi over 2. That's going to be 0. So 0 plus, and then sine of pi over 2 is 1. So 0 plus I. Again, going back to that unit circle. Okay, multiplying this out, we get 0 there, 0 here. So it's basically root 2 over 2 I squared and I squared plus root 2 over 2i. This is negative because there's a negative times a positive. I squared becomes negative 1. Negative 1 times negative gives us root 2 over 2 plus root 2 over 2i. Again, going back to that unit circle, I know that pi over 4 gives me the root 2 over 2's, the reference angle. I'm going to say alpha. Both of these are positive, so cosine is positive, sine is positive. So we're looking at quadrant 1, and quadrant 1 means that our reference angle is the same as our terminal angle. So I can now say that this is 6, because this is my r, 6 CIS pi over 4. Because again, we are in quadrant 1, and I know this because both my sine and cosine are positive. Okay, I'm starting to see a pattern here, because when I multiplied the first two, we got 4 cis 0. And when I multiplied these two, we got 6 cis pi over 4. And the pattern I'm seeing here is I multiply these two coefficients, and then pick a different color here. Can I see this? That's a little bit hard to see. We'll pick this pink. Then between these two, it looks like I add them. So if my hypothesis is true, if I do 2 times 2, that's going to be 4. Then write the word cis, and then pi over 4 plus negative pi over 4 will give me that 0. So that works out there. Let's try the second one. 2 times 3 is 6. Negative pi over 4 plus pi over 2 is pi over 4. So that seems to be working out. That seems to be working out in our favor. But let's see if this happens for any value. So for any value of r, any value of a, multiplied to any value of x or s and any angle b. So what I'm going to start with, and again, this is the proof part of this. is that if I have Z1, and Z1 is equal to R CIS alpha, and Z2 is equal to S CIS beta, two different angles. If I multiply them, what I get, that idea of you multiply R times S and add alpha times beta. So let's try this. I'm going to use a baby blue for my colors in this case. So I'm going to look at R. This one is going to be cosine alpha plus I sine alpha times S cosine beta plus I sine beta. Okay, again, I could do R times S, so I get R times S. Then multiply through FOIL. We're looking at cosine alpha times cosine beta. Then I'm looking at I cosine alpha sine beta plus I cosine alpha sine beta. No, other way around. Don't look at that. Other way around. Cosine beta sine alpha plus I squared sine beta sine alpha. I should have led with alpha. I just start writing beta instead. All right. So looking at this now, it looks like we have R times S cosine alpha. Again, I'm just going to rearrange these. Beta. This is going to be a -1, so it's minus sine alpha sine beta. And not sine beta. And then we have plus I, combining those two, cosine alpha sine beta plus cosine beta sine alpha. A lot of alphas and betas in there. And then going back to the sum formulas, remember the sum formulas if I had cosine alpha plus beta, this is going to equal cosine alpha plus cosine beta. So we're going to go back to that, and basically that's what this is right here. So RS, and we're going to look at, actually there's more to this. Cosine alpha sine beta, which is, this was the identity here was cosine alpha cosine beta minus sine alpha sine beta. And so this is equal to this guy, which is cosine alpha plus beta. So difference, no, sorry, the sum formulas that we found in earlier equations for trigonometric functions are the sum identities. Okay, so then we have that, so that takes care of this guy. This one, again, we're adding here with cosines and sines being opposite here, which tells me we're dealing with a sine identity. So this is plus I sine alpha plus beta. And so we are left with this alpha plus beta being the thing that we're adding. So we're left with that formula. It does work for all values. Since we have the same angle here, we can say this is alpha plus beta. And by the way, this one right here is going to be sine alpha plus beta, if you remember that identity. All right, so it is true. It is true when I multiply two different polar formulas or polar functions, we actually can multiply the r's in front, or the r's and s's in this case, and then add the angles inside. So this is true for everything. This will be a great formula for you to have for multiplying two complex numbers. I box it. I would star it. This would be something great for you to remember. All right, so we survived through the proof for this. We came out with a formula for this. So make sure you have this in your notes. If you need to pause this video to do that, please do so. And I will catch you in the next video.